So welcome everyone to today's session of Seminario Flotante. Our speaker today is Samaria Montenegro. She's a professor at the University of Costa Rica, and she will be talking about definable groups in partial differential fields with an automorphism. So thank you, Sami, for accepting the invitation, and the screen is all yours.
Thank you, Dario. I am always happy to speak of math in Bogota, even if I am not in Bogota now. So I will speak about definable groups in partial differential fields with an automorphism. And this is a joint work with Ronald from the University of Costa Rica, with Zoe from the CNRS of Paris and the École Normale. So the idea is that I want to speak about definable groups in some kind of fields that I will explain later, and I will give you all the details that you need. But there are some fields who have derivations, many derivations, and also an automorphism. So to understand that a little bit, and even if maybe you don't know a lot about this theory, I will give you all the preliminaries that you need. So, and I see some students that I am not sure if they know or not differential closed fields. So we're going to speak a little bit that what we know in the case of we only have derivation, and what we know in the case of we have an automorphism, and then how can we mix the two things. So to be sure that anyone is in the same context, that derivation is a map. Well, I am always interested in fields and in fields of characteristic 0 in my talk, okay? So a derivation is just a map that satisfies two things. So the derivation of a plus b is equal to the derivation of a plus derivation of b, and the product of the derivation of the product of a, b, that will be a derivation of b plus a derivation of a, b. Okay, so you can do algebra in this kind of fields, and the algebra of fields with m commuting derivation. When I say commuting, that's mean that little like commute between the derivations. So if you have, for example, two derivations, so that means then delta 1 of delta 2a, that will be delta 2 delta 1a, okay? And for all the possible derivation that I have. Okay, that was a study for a lot of people, and I'm kind of sure that I will forget people, but that was in particular developed by Reed and by coaching. So the idea is that you can do the same that we do with algebra. We can define polynomials, but in the sense of differential polynomials. I will kind of give you some details. So you have, when I say delta field, so we fix delta as set of derivations, and we say that a field is a delta field if the set delta is our derivation in the field and all the derivation commute in that field. Okay, so when I say delta field, I assume that the derivation are commuted. We have the ring of polynomials, of differential polynomials. So, and I will denote that by that k of y delta, that will be the rings of polynomial in that variable. So the idea is that now I have variables with a lot of derivation, and power of that derivation, the power will be positive. That will be the new variables of my polynomials. And the elements of this ring that we'll call the delta polynomial. And of course, in the same way that we can have topology, in the same way of algebra that you have the Zariski topology, here we will have Colchin topology, and the idea is that the set of zeros of delta polynomials in some kn, there will be the basic closed sets of that topology, and that topology is also kind of nice. It's Noetherian, it's a Noetherian topology, and it's really nice. So you have the analog of the things that we already understand in the sense of algebra, but now in the sense of differential algebra. So you can define an delta ideal, you can define an variety and delta variety, and you can say that this is delta irreducible, and all the things that we can do in the algebra. Okay. So if we want to study these fields, but in the sense of model theory, we need to be clear in what language we are working. So you fix, like always, when we work in the field, we fix the Lagrangian rings, and we will use also a function symbols for each derivative that I am interested in. Okay, so I will fix an delta and set of derivation, And I will work in the language L delta, that will be the language of rings with all the deltas, okay? So we want to study the delta fields in the sense of model theory. And in the case of M equal to 1, that's means that I only have one derivations in characteristic 0. The work was started with the work of Abraham Robinson and of Leonard Bloom. Maybe I am forgetting people, it's possible, so sorry. And in the general case that was shown by Tracy McGrail, that in fact, the L delta theory of differential field of characteristic 0 with M commuting derivation has a model companion, which we denote by DCFM, okay? So this theory, what we know about this theory in the sense of model theory, this theory is the same idea of the ACF fields for the case of fields, okay? So it's close, but now for the differential polynomials, okay? So it's a really nice theory. What we know, it's complete. So this is nice. It's omega stable. This is really nice. So we have all the good properties about omega stable theories. So we have a good notion of dimension and of independence, and we don't have a lot of types. So it's kind of nice. For example, the independence, the non-forking, that will be given by the independence of algebra, the linearly disjoint thing. We know that the theory eliminates quantifiers, of course, in the language with the derivations. And we have also that the theory eliminates imaginaries. So in fact, this is a nice theory. They have a really good properties. And the models of this theory are called differentially closed. Okay, again, this was exactly the analog that we have between fields and algebraic closed fields, now between delta fields and differentially closed fields. So it's kind of the same analog and the same idea. So this is really nice in model theory. We want to understand a little bit what happened with the groups. And to do that, before that, I will give you some basic definition in the same way that you have algebraic group in the sense of ACF. So here you have delta algebraic group. It's kind of the same analog always, and you just change polynomial for delta polynomials and variety for delta varieties and ideal for delta ideals, and you have kind of the same stuff. So a delta algebraic group, that will be a subset of an affine space, which is both a differential variety in the sense of Colchin and Reed, so that in that sense that you really, it's exactly the same idea, and whose group law are morphism of differential varieties. And by quantifier elimination of the theory, in fact, we have that the delta algebraic group that will be really close related to definable groups, and exactly in the same way that algebraic groups are really related to definable groups in ACF. So this is the same analogy. So we can do the same. So now we have, if you take, for example, a delta algebraic group, what will be delta sample? Again, it's the same analog. So that will be a group who is not commutative and has no proper connected normal delta closed subgroup. When I say delta closed, that means closed for the Cauchy topology that I just defined before. Okay, and you have, for example, a delta sample group if has no trivial connected normal commutative delta closed subgroup. It's the same idea. So you have the notion of sample groups in the usual notion, and now we have the notion of delta sample or delta semi-sample, okay? So the idea and the inspiration of our work was this Cassidy theorem. Cassidy studied a lot about the differential closed fields with M derivation. I think she was a student from Colchin. If I think this is true, but I'm not completely sure. But in any case, that was the theorem that was the inspiration of our work. We want to do the same of this theorem, but in the case that we have also one automorphism. So what is this? What is the theorem? So we fix an monster model of this DCFM, and we will take H that be a sample algebraic group, okay? And we will take a definable subgroup of H of U, okay? That's mean a definable subgroup of a sample algebraic group, but in the rational points in this model, okay? But also we will suppose there is Zarinsky dense inside H, okay? If you have all that, So the idea is that I am describing the definable groups inside a sample group. So you will, she proved that in fact G is definable isomorphic to H of L, where, and this is important, so remember that H is algebraic, but L, that will be the constant fields of a set of commuting derivations. In fact, L, that will be definable, and delta definable in our model. And maybe I didn't say that, but a set of, a constant field is a subfield such that E is 0 for all the derivations, okay? And that will be a subfield of the field. But in any case, the thing that is important here is that this L is a subfield of U that is L delta definable, okay? And furthermore, the isomorphism that will be given by a conjugation of an element of H of U. So what do we know about that? That means that in fact, the definable groups inside a sample group are really, really similar to an algebraic, to the sample algebraic group, okay? That is what a grosso modo the Cassidy theorem says. So the idea is that we want to reproduce these kind of results, but now in our context. Our context is that we have the derivation, but also that we have the automorphism. But even before that, what happens if we only have one automorphism, just to be sure that the theory is not really more complicated. So you take, if I only have a field with an automorphism, I will call this field difference field or sigma field, okay? If I work in the language L with, L, the language of rings with a symbol for the automorphism, it's true that there is a model companion of the sigma fields and they will denote it by ACFA, okay? So this theory that was studied for a lot of people, in particular for Zoe and for Udi, who really studied the model theoretic properties of this theory. I will give you a resume of that. So what we know about this theory is also model complete, so this is nice. It's not stable, so it's more complicated in the sense of model theory that differential closed fields, but it's super sample, so it's not too bad, okay? We have that eliminates imaginary, so this is nice, but it's not complete. Why is not complete? Because maybe you can extend the automorphism in different ways. But in any case, you can obtain the completion if you describe the isomorphism type of different subfields, the algebraic closure of Q. Though in any case, you know what are the completions, even if there's not complete. And the other thing is that you don't eliminate quantifiers, so the definable sets are a little bit more complicated, but in any case, we know more or less how are these, okay? So
may I ask a question, Sammy? Sorry.
Yeah.
So usually when you eliminate imaginaries, you have to add some sorts. In this case, you don't have to add any sort?
You have elimination of imaginaries in that language, yeah.
In the same language, okay. And same happen with the differentially closed fields?
I think, yeah.
Okay, thanks.
So in any case, so that's theory. You can see that if you have an automorphism, even if you don't have derivation, so that's it's a little bit more complicated in the sense of model theory. So now you don't have quantifier elimination, so now you are not stable, okay? So now you know if you have derivation R and you have also an automorphism, that will be not that easy as differential closed fields. So what do we know about definable groups only with one automorphism? So a version of Cassidy theorem was proved by Chatzirakis, Hrushevsky, and Peterson, and it's kind of the same idea. They prove, in fact, that was more general, and I just put the version of the Cassidy theorem that I need now. But the idea is that they prove exactly the same. In fact, we have an almost simple algebraic group defined over, well, suppose that this is a model of ACF. So they prove that any proper definable subgroup of H, which is Zariski dense in H, is definable isomorphic to a subgroup of these kind of things. But okay, I am in characteristic 0, so in fact, I don't care about that. So the idea is that we are definable isomorphic and subgroup of rational points of the algebraic simple group, almost simple group, but the rational points of what field? of this field that will be the fix of some power of sigma. So in any case, we know that the definable groups inside a simple group are really, really similar to the rational points of...
Okay. What is almost simple?
Almost simple is in particular way, because I always forget all the definition, and I say definition who are implies in any case simple algebraic group that it has no proper connected algebraic subgroup, just to be sure that I am not giving you a false definition. Because I can't.
So you allow a finite center.
Yeah, we allow a finite center. Thank you, sorry. I got it's okay. I erased the thing.
So one question about this, Samaria. So in your description of ACFA, there is also a very nice independence notion there. Is there? I think you it is. I mean, it is not. I mean, it's outside of stable. It is super simple, but it's still. You can still kind of control.
Yeah. You have all the independence that will be also related with the algebraic disjoint of the algebra. Yeah.
But there is something about the M here that for some integer that you have to iterate the sigma here and the Frobenius or Frob n or something.
No, in our case, you can really forget the Frobenius because I am in characteristic 0 in that.
In the DC, okay, yeah, in your case, yeah.
So just forget. I don't know why I put the Frobenius there. Just forget.
Okay.
I think in characteristic 0 that I am interested on in characteristic 0. That will be just that the definable groups inside an almost simple group that will be really similar to the rational points of some algebraic group, but the rational points of a field who will be the fix of some power of sigma for some m. Okay. So now we want to mix. We want to mix all that. So we want to have some, because in model theory we like this kind of stuff. So we want to mix what happens if we have derivation and we have an automorphism. Okay. So of course we can mix derivation and automorphism. So take a delta and fix of derivations, and take an automorphism and take your language that have the rings and the derivation of the automorphism and everything that you want. Well, maybe not everything that you want, but in any case. So, and I will say that a delta sigma field, that will be a delta field. Remember that for me, delta field, that means that has the derivation, and also that the derivation are commutative. So a delta sigma field, that will be a delta field with an automorphism that commutes also with the derivation. So everyone is happy and everyone commutes and everyone is friend and it's really nice. Okay. So we have some derivation and we have one automorphism. We can also ask the following question: if we can, why only one automorphism and not 2 or 3? So the thing is, the model theory of the of the fields with more automorphism, that will be much more complicated than this one. I will speak a little bit later, but in fact, they don't have. This is not even model complete. That doesn't have a model companion in the case that you have more automorphisms than one. But I will speak maybe a little bit later. But in any case, if you have derivation and one automorphism, you can also have polynomials, and you can do algebra and everything like always. And you will have a ring of polynomial and delta sigma polynomials in the same way. So you have this kind of variables who has now it's exactly the same. So now you have the derivation with some powers and also the automorphism with some powers, and that will be the new variables of our polynomials, and that will be also a nice topology and sigma delta topology, such that the zeros of this topology will be the zeros, the basic closed sets of this topology, that will be the zeros of sigma delta polynomials in some k of n, and that will be also not zero. And in fact, it's a kind of the same. So we do the same, and this is really nice, and we have nice topology, and we have nice properties, and we can define everything in the same way. What we know about model theory. So we know that the meets and model companion, that was shown by Ronald, who is somewhere there, in the case of m equal to 1, if in 2006. And in the general case, that one shown by Leon Sanchez in the general case. So if you have M commutative derivation and one automorphism. So of course, this theory that will be much more complicated than only with derivation because you have an automorphism. So it's model complete. Of course, it's not omega stable because you have an automorphism, but it's super sample. And eliminates imaginaries, of course, is not complete, but the same argument that in the case of ACFA. And of course, you do not eliminate quantified for the same argument. But in any case, it's not too bad, okay? If the completion are obtained in the same way that ACFA. So the idea is that we want to generalize the causative result for our context. So we want to understand what are the definable groups in that case, in that theory, okay? The main theorem is that, so it's kind of the same idea. So you have a simple algebraic group defined over the rational, and you have a definable subgroup of the rational points of the group, okay? Exactly the same as before. So of course, we suppose that it's a Zariski dense inside H. So you have your G, who will be a subgroup of H of U, and H that will be a simple algebraic group defined over the rational, who is Zariski dense. This is Zariski dense, G is Zariski dense in H. So now we will describe not G, but G zeros for some G0 of finite index inside G. So it's not kind of sad. So it's kind of sad that we cannot describe the group, but we can describe the group modulo and finite index subgroup. And we prove that in fact there is some G0 and subgroup of finite index of G, which is conjugate to a subgroup of H of K, such that K is equal to L for some L delta definable subfield of U, or K that will be the same idea. So the fix of some power of sigma intersection with L for some R the power of sigma. So Dario.
Sorry, I mean, I guess you're going to go through the proof or something, perhaps.
I will give you some details.
I wanted to ask you just before, just to have a better idea. So I know, I mean, correct me if I'm wrong. I know that ACFA is super simple of rank omega, right?
I know what, sorry?
That ACFA, ACFA, is super simple of rank omega. Is that correct?
That's true. Yeah.
And what is the rank of this DCFA? Do we know it?
I'm not sure if we know exactly the rank side.
Omega squared.
Yes, it's
So it's omega times omega.
Yeah,
no. It depends on the size of delta. So if the size of delta is m, then it's omega to the m plus
omega to the m.
Plus omega. Okay.
Omega
okay. Thanks.
m plus
Plus 1 to the m plus 1. Yeah.
Yes.
For m derivations.
Of course, that will depend of the number of derivation. Yeah.
Okay. Thanks. Sorry.
All right. So the idea is that we arrived to prove that in fact, it's kind of the same result of the case of ACF. So we know that there is some definable subgroup of finite index of our group, who is really similar to the rational points of the sample group for some field who will be definable, delta definable in any case in our group, and who will be or a definable subfield or the fix of some power of sigma intersection L. Okay, so I don't want to give you the proof of that, but I will give you some details about that, some ingredients of the proof. So the idea, in fact, is that we will use causative result for another group, so for the Cauchy closure of G, and then we will do exactly the same idea of the proof for the case of ACFA. So this is the idea. So we may assume that the Cauchy closure of G is connected, and then we need to go to some finite index subgroup. But in any case, we can assume that. Of course, that will be the Cauchy closure of G that will be dense in H, and we will use causative result in that group. So we obtain some L subfield of L, who will be L definable. So now we have the G of delta that will be conjugate to H of L for some L who will be and delta definable subfield of U. Okay. So now that we use Cassidy, we will follow the proof, the same idea of the proof of AC if A. So we need two cases. In the case of the first case is if we don't have center in H. So we define something that is the prolongation. This is exactly as in ACFA. So you take for each n, we define that prolongation P of n, that will be a map between HL to this product. So in the product, you have phi of L, product sigma of H of L, product sigma square of H of L, and dots, sigma n of H of L. So you have this prolongation, of course, that you take, the map is to take our G and you send the G to the tuple of G, sigma G, blah, 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 sigma n of G. And we will take G of n, that will be the Colchin closure of Pn of J. So that means you take the image of G, you take the Colchin closure of this thing, and that will be G of n. Okay? So you take the image of G inside the product, then you take the Colchin closure of that, and that will be the thing that I call G of n, and that will be for n. I do that for any n, in any case. So looking at our hypothesis implies that this zero is of the form of H of L. Okay, so wait. So now I will take n minimal such that satisfy that G of n. Remember that was the image of G, the Colchin closure of the image of G. So I take some n minimal who is different to the product of the right. Okay. And in that case, we can show, and that you need to believe me because I will not give you all the details, but you can show that in fact, G of n is in fact defined by a particular equation. Somehow an equation that will be sigma of n of G equal to delta prime of G. Okay. But the important thing is that this delta prime of G, that will be a morphism who between H of L and sigma n H of L. Okay. So in fact, looking at this in the left side, you don't have derivation. So you have all the things that come from the derivation are in the right side of this equation. Okay. And we can prove, in fact, that we use some results about sonnets, but in any case, we can prove that in L that will be equal to sigma n of L. And so that implies that this theta, that will be in fact an automorphism between H of L. Remember that H, that was the sample algebraic group of the beginning, okay? And now for a little bit work, now it's more technique, but you need to believe me a little bit, but the idea is that with a little more work, we can prove that in fact, G is conjugate to a subgroup of some power of, for some air, a subgroup of H of the fixed sigma air of L, and the field that will be this L that we find with Cassidy. So this is exactly the idea. An important thing here is that, in fact, we do that. We use Cassidy theorem for the Colchin closure, and then we do the same that in the case of one automorphism. Of course, we need to be sure that everything is fine. So we have something who is a little bit more general, but to do that, I need to define something that will be important later in any case. So we define some notions of the notion of definable quasi-sample and the notion of definable quasi-semi-sample. But the idea is if you just have a definable group, we will say that is definable quasi-sample if G has no abelian subgroup of finite index, and if whenever H is a definable infinite subgroup of G of infinite index, so the normalizer that will have also infinite index, okay? This is the same in the case of definable quasi-sample, and in the case of definable quasi-semi-sample, it's kind of the same. If G has not a abelian subgroup of finite index, and also if whenever H is definable infinite commutative subgroup of G of infinite index, then the normalizer has also infinite index. But in any case, why we define that? So the idea is that in our context, maybe a definable group has infinitely many subgroup of finite index, okay? So what is the idea? This notion is really nice because the notion is preserved for going to a subgroup of finite index, and this is also preserved for quotient with finite centers. So this is the dilemma that proves that if you have a group and you have an undefinable subgroup of the group of finite index, and if you have also set with the finite and normal subgroup of G, so if G is definable quasi-sample, this is equivalent to G0 definable quasi-sample, and also this is equivalent to G quotient to set definable quasi-sample, and everything is also true for a quasi-semi-sample. So these are notions who are good because comes from the quotient and comes from the subgroup of finite index. So we have this theorem who says the following. So the idea is, remember that in the first theorem of custody, if we are inside a sample algebraic group, you kind of understand the definable group if you are inside some nice group. So in this theorem, so we just have a definable group who is quasi-sample or respectively quasi-semi-sample. So you will find a definable subgroup of finite index of him, G0, who will be delta sample or respectable delta semi-sample. And you will find also this H that will be a delta algebraic group over Q and a definer of homomorphism between the part definite the subgroup of G of finite index and the rational points of this nice group. Okay? So that's mean that in some way, if you have a group who is definable quasi-sample, that will be really similar in some way, and delta algebraic group and a delta algebraic group, and the rational points of a delta algebraic group. And what is this important? Because, well, I will give you quickly some ingredients of this proof, who is in fact not difficult at all, because it's kind of that comes immediately from a result, a more general result of Blossier, Martin Pizarro, and Wagner. They prove a general theorem about theories that satisfies that are one-based, but the idea is that in our case, what that means, we know that DCFM or A, it's one-based. I will not give you what is one-based, but it doesn't matter. It's one-based over DCFM, and DCFM is omega stable. So they show that in that case, in particular for our case, there exists undefinable subgroup G0 of our group G of finite index and delta algebraic group H and undefinable homomorphism between G and H of U with finite kernel. So in our case, we only need to prove that, remember that our G that was definable quasi-sample. So in our case, the only thing that we need to prove if G is definable quasi-sample, so we can assume that the H that we find is in fact delta sample. And in the case of definable quasi-sample, that the group H that will be delta semi-sample. So in any case, what we have, in the moment that we have a definable group, even if you don't know if he is inside or not a simple algebraic group, in the moment that you have a definable group who is quasi-sample, you manage to know that there is some subgroup of finite index of this group, who is kind of similar to a delta algebraic group, okay, in some way. And now we put the two results together and we obtain a strong result that is kind of long, so I will just put everything there and I will try to not be technical, but this is the same idea. So we take the first result and the second result, and you take an infinite group definable in the model of DCFMA. Suppose that this group is definable. Quasi-sample. So we prove that there are an algebraic group defined over the rational, a definable subgroup G0 of G of finite index, and a definable group homomorphism between this subgroup, who is big in G, and H of U. So in any case, so you have your group, sorry, maybe ignore everything. So you have your group. You have that who is definable quasi-sample, so this is important. So with that, you can find H. who is really nice example, algebraic. You find your age, you find a subgroup G0 of G big, of finite index, and you can find an homomorphism between the subgroup G0 and the rational points of U with the following properties. So the kernel one that would be finite, and the Colchin closure of the Colchin closure of the image of G0, it's H of L for some L who is a differential closet, and that will be definable in the field. Or either you have that the image of G0 that will be H of L for some L who is definable, delta definable, or for some L you have the phi of G0 that will be a subgroup of this thing. So exactly the same of before, hash of the fix of sigma L intersection with the field L. So in any case, so this kind of, I don't know why I put this slide in that way, but the idea is that we can put the two results together, and if you have a definable quasi-sample group, we can put this group inside a simple algebraic group and more or less describe this group, and I say more or less because modulo and subgroup of finite index. So that is the idea. Okay. The next slide, it's really a mistake because it's horrible and I don't know why I decided to put this slide here. It's kind of technical, but so I will just go quickly. In the same of semi-sample case, you can do the same. So it is kind of, it's the same idea. It's just more complicated and you have products of group, but any case it's not really important. So you have a definable group who is undefinable subgroup of some semi-sample algebraic group. But in any case, the idea is that you can describe a conjugation of the group, and you can put the conjugation of the group between the products of some groups G. This you can find this kind of group that will be subgroups, normal subgroup. This will be each E, that will be a normal subgroup of that. A conjugate of our group G that will be in the middle. And so everything is kind of fine and everything has finite index, and it's too bad. And I don't know why I decided to speak about a semi-sample cause, but it's kind of the same idea, but now you have some products of sample groups and not only everything inside a group. Okay, so this is the first part that I want, the first case that we want to talk. So that was in fact the generalization of the Cassidy result that I present you in the beginning. So I will speak quickly of the connected component because I will not speak a lot, but the idea is that inspired in the results of Hrushevsky and Pillay for groups definable in pseudo-finite fields, we then dare to show that definable groups which are definable quasi-sample have as small as definable subgroup of finite index. So looking at this small definable group is called the connected component. It always exists, but it's not true that that is always definable. So we'll see that in our case that will be true, but if you suppose that our group is quasi-semi-sample, okay? So in that case, that will be true. So the first theorem that we prove is exactly the same idea that proved Hrushevsky and Pillay. I just forget. Yeah, Hrushevsky and Pillay. So it's kind of the same idea. So you have that was the result that we proved. You have an algebraic group, and you have a subgroup who is Zarinsky dense, who will be a subgroup of H of U, Zarinsky dense and definable, which is properly contained in the sigma delta closure. Okay. Of course, we have the notion, maybe I didn't say that, but you have all the notion of closure for sigma or for delta sigma, okay? Then we can find and quantify free definable subgroup R together with a quantified free definable map between the group R and the sigma delta closure of G. such that the image of R of U is contained and of finite index in J and with the finite kernel in R. But in any case, so that's mean that we can describe, we can understand a little bit what happened inside the algebraic group, okay, for the groups who are definable and Zarinsky dense. The proof of that, it's kind of the same. We put together some results about Pillay, who did some kind of configuration groups. Now we need to do the same idea, but in the case of we have derivation and everything. So, and we more or less, it's a real technical proof, but it's similar in the case of the theorem of Pillay and Khrushchevsky. So in fact, we kind of understand the connected component. I will not explain a little bit that, but this theorem is that describe a little bit what happened with G0, that will be the smaller definable subgroup of finite index. So we know that there exists in the case of quasi-sample, but in fact, we kind of describe the thing. But the important thing that, because I don't want to be really technical of this, is the corollary. So we prove that in the end, if you have a definable quasi-semi-sample definable group, so now if you have this kind of weird definition that I give you in the beginning, then G has a definable connected component. So remember that when I say this always exists, but it's not always definable. So in that case, it's definable, but we need to assume that it's quasi-semi-sample definable group. So this is what I want to talk. So there is some question that you can ask, for example, it's kind of, it's possible or it's not possible to do similar if you have more automorphism. The model theory of a fields with some automorphism and is much more complicated. It doesn't even exist a model companion of that. But we are trying to do something about that. So maybe this is a spoiler for the future, but we are working on in at least understand a little bit what happened, what we can say in the case of we have a lot of automorphism. But I think I will, in any case, finish here. So thank you.
Thank you very much, Sami. Does anybody have any questions for Sami?
Laura.
No, I think she's just uploading. But Juan Felipe has a question.
Juan Felipe has a
so
question.
Go ahead.
Yeah, so maybe you can give us an idea of how to build this H. I mean, you start with definably quasi-simple G group, and you find an H which is, if I understood correctly, a real simple group to which it is there is an isogeny to it. So, and you're relying on previous results, but there is like an intuitive way to build H. You know what I mean? Like if you start with,
you say in that,
how do you find H?
Yeah, in fact, well, where is that? No, it's say. You say that, no?
Yeah, exactly. So
yeah, in fact, the thing is,
constructive way to find H.
We really use the group that they find. That was a really general result that proved these guys. Really general result that proved Brosier, Martin, and one that give us our group. I don't know exactly now what was how they do. Maybe so I remember with more details of me that proof, but I am not really sure about how they exactly find this age now.
Okay, so it comes from the result for delta algebraic groups.
No, the
connected component.
The L, but I think Juan Felipe says that in the case that we find this H algebraic group, so you take your group and you find, using the fact that we are one based, you find in fact our H algebraic group who is inside such that G is definable here. But I don't really remember. I read that with details later before, but I don't really remember of the details of how they find this G, this H. Sorry.
Okay.
I think
Thanks.
it's a bit like how do I say this? I mean, it's sort of, it's like the proof in ACFA, and it uses techniques of that Kowalski and Pillay developed for ACFA.
Okay.
And it works. I mean, they sort of found a general framework where it could be generalized to all kinds of theories. But I think the how do you say, the inspiration comes from this paper of Pillay and Kowalski. Kowalski and Pillay.
Thanks.
Okay, more questions for Sami? I do have a small question. I mean, it's probably related with what Juan Felipe just asked. But you were saying basically, I mean, in the main term, you started with a definables group, G, and then you find this group of finite index G0, and then G0 is the one that is isogenous to an algebraic group, right? Do you know what happens in this finite action between G and G0? Like how can you describe, or what would be the problem to generalize that to, for example, having an isogeny from G to H?
The problem is that in our case, we maybe have infinite definable subgroup of finite index. So this is main problem always. So we cannot arrive to we need always to pass to one subgroup. Well, not always, but you cannot arrive to describe the big group in all the cases, and it's kind of the same idea of always. So maybe we have finitely many subgroup of finite index, and maybe we need to go to a subgroup of finite index.
But do you have an example where that pass is necessary?
And you say a specific example?
Or just an explanation of why you have to pass to G0 before going to the isogeny.
Some way we need to really, for example, have some. Now I in my mind I don't have any specific example of that. I didn't have. I have a lot because I have a lot of problems later, but in the beginning. So now I don't have any specific example of that. Maybe.
Okay.
I am completely blocked now, but I will tell you maybe later.
Worse.
I have another question. Sorry.
Go ahead.
So this is from regarding the completion of the theory. I mean, once you fix the isomorphisms type of the automorphisms, this theory is complete, right?
Yeah.
So
yeah. If you know how to extend if you describe the type of isomorphism in the algebraic closure of Q, so the theory is complete. So always we work in the completion of the theory. So the theory
does it have a quantifier elimination?
We don't have quantifier elimination in any case, but we understand the definable the definable sets even if you don't have quantifier elimination, because you know that there are a Boolean combination of formulas where exists for something who are positive and differential equations. So even if you don't have quantifier elimination, the definable sets are not too bad.
Right. Okay.
So do you have a quantifier elimination up to one existential formula or something like that?
Yeah, okay.
More or less. Well, yeah, it's more or less.
Okay.
Everything. You don't have quantifier elimination, but you know that the definable sets are Boolean combination of stuff who have existential stuff more, and then positive formulas who are really nice and comes from delta polynomials. So it's not too bad. Even if you don't have quantifier elimination, the definable sets are not too bad. We kind of understand. And even if you are not complete, it's not bad because you understand what are all the completions. So it's not like you don't know anything. So
yeah,
this is, in fact, this is a nice theory in that way, even if you don't have
So I just one kind of so you said the Cassidy theorem was part of the the big motivation of your work, but in the Cassidy theorem the definability issue seems not to be central. I mean, you have like a definable version of the Cassidy.
This is important what you say. In fact, the paper of Cassidy, it's completely different right that I give you. So that was a really big and hard work to understand the Cassidy paper, because that was with a completely different notation. In fact,
She's not a logician.
In a completely different way. So there is some stuff that they call Chevrolet group, and the proof was with Lie algebra of differential groups, and that was complicated to understand what that means, what her results means for us. So you are right. So the Cassidy theorem, it's completely different in the way that she writes the thing. So the theorem that I give you, that was the traduction for our result. But of course, yes, you are right. That was not present like that in the Cassidy paper, and a big part of the work that was to understand what happened in the Cassidy paper, because that was, for us, that was completely a different form to write the things. It's completely different. So. But in our case, that was the traduction of the thing that we wanted. But the Cassidy paper is completely different.
But I understand that Cassidy is trying to, I mean, among other people, but in her seminar, to do the Galois theory of differential equations in general, and for M, delta, and so on.
She did a lot of things about that, but a lot. Yeah.
But this theorem seems like a very central theorem in a general Galois theory sense. I mean, it looks like a Galois theory theorem, but for this, so you see a hope of kind of continuing with your techniques, definability and all these, based on Martin Pizarro, Lussier, this, and kind of pushing in the direction of where the people in the Colchin seminar, in Cassidy's work and her group, they have been going. Do you think it is possible to do kind of a parallel Galois theory with pure model theory up to some point, or
yeah,
the limits of that? Or
yeah, I think it's possible. I need to say that for me, that was really complicated to understand the notations and everything of Cassidy papers. In fact, that was in particular the same. This is the first time that I work with differential fields. I always work with PRC fields, I always speak about PRC fields in any seminars in Bogota. So that was also differential fields. I kind of, in that moment, I didn't know about. But in particular, Cassidy theory was completely different. It was all the notations were completely another thing for me, even. So that was, and even for Ronald, who works in differential fields, I think that the notation are not.
Yeah, because it's like Colchin. She reads like Colchin because she was her student. So it's really a really awful notation. And besides, there are references for example, in Pile's works, and he says that this is a version of Cassidy's theorem, but he doesn't give a precise reference and no translation whatsoever. So it was kind of complicated to understand that mostly, because in fact there are two long papers to go to this theorem, and so yeah, we had to read a lot before. But I think that there's some work on Galois theory on ACFA, which is not that nice because there are some problems. I mean, for DCF, for differential closed fields, there's nice Galois theory that I think Pile developed, and maybe Kowalski. But with ACFA, there are some problems. I think this is not so elegant a theory, but we haven't looked so much to that direction yet.
I have a final question very quickly. Did you use explicitly super simplicity of the theorem, like since it is super simple, then this and that.
We use some utils about super simplicity to super simple. I just wait. I don't know if I am. Did you listen to me?
Yes.
I
Yes.
wasn't sure if I just go out of this session of Zoom. We use simplicity in particular in a lot of places because we need to be sure that there's some notion of, for example, independence, and they think that one base it on. So we use simplicity. Yeah, it's a lot in.
It's a key ingredient. Okay.
Yeah, yes, for example, to apply the Lossier-Scanlon-Wagner theorem.
Yeah, that we need.
Yeah.
You need.
Okay, any more questions for Samaria? If there are more questions, then let's thank Samaria again for the talk.
Thank
Gracias,
you.
Samaria.
And yeah, we'll see you, I guess, next. Let me just check. We'll see you next Wednesday in the talk by Laura Gamboa, right? So
And we come back to West night in the afternoon.
yes, it will be Wednesday afternoon at 4 p.m. I'll make sure to send the invitation correctly this time.
Thank
Okay,
you.
thank you. Bye.
Okay.
Bye.
Bye.